In this video, I'm going to begin a discussion on scattering theory. And so in quantum scattering, we're going to have to look at a particle, which is a wave, scattering off of a potential. And so to start, we'll first do a little primer here on classical scattering theory. So this would just be things like pool balls bouncing off each other, or a golf ball bouncing off of a bowling ball, or things like that. And so scattering a projectile with energy E, so it's going to have some kinetic energy off a positive potential. So you could think of that like the potential being sort of the hardness of the ball that you're scattering it off of, and so it's centered around a scattering center, and so that would be like the center of the bowling ball, for instance, that you are scattering off of. And so I keep using the bowling ball thing because we want to assume that the scattering center of mass is a lot greater than the projectile mass. And so we want to think of, like a heavy bowling ball as the scattering center of mass. And then the projectile would be something maybe like a golf ball or something like that. And so the scattering angle theta of the projectile is the angle between the straight path from the approach and the straight path from the scattering. And so by the straight path of the approach, I mean, so we have the projectile coming this way. And so it's going straight until it gets to this potential, and then it will scatter off of it, and eventually it'll get to a straight path going this way. And so that we have the projectile angle straight, the straight path of the projectile over here, then the straight path from the scattering over here. And so you can think of, if we're using our golf ball and bowling ball example, then this right here would be the center of the bowling ball. And so this probably wouldn't be as smooth of a line because our golf ball would kind of come, it would hit the bowling ball there and then sort of bounce off of it that way. But we can also think of, I mean, when we get to quantum mechanical systems and we're thinking about, say, like a particle, then we're thinking of a potential, which would be like a repulsive potential, and so there'd be more of a smooth curve this way. But what we're interested in anyway is just the angle between this right here and this right here, which will be our theta right here. And so the scattering we can see is dependent on what's called the impact parameter B, which is what we have right here, which is the offset of the projectile path from the scattering center. So we can see that if our B was like over here instead, we probably wouldn't get as much scattering going on because the potential would be it'd be further away from the potential, so the potential would presumably be weaker there. And we can think of it too in terms of our sort of golf ball, bowling ball system. So we have our bowling ball here and we're shooting our golf ball here. If we shoot it from somewhere up here, it's going to bounce off right there and kind of go that way. But if we shot it from like right here, we see that it would bounce and kind of go that way. And so the angle, from here to here is going to be less than the angle from here to here, and so that impact parameter is going to determine the angle from which it scatters. And so if the potential is a hard surface, as we've been talking about, like a bowling ball of radius r, then our potential would look like this. So the potential is effectively infinite inside the bowling ball and then zero everywhere. And so that is that idea that, if our our golf ball here is moving towards our bowling ball here, it'll bounce off if it hits it. But if it's far enough above it, if our impact parameter here is large enough, then it will just keep going straight because there is going to be no potential that we run into here. So yeah, we get something that looks like this. And so this is the hard sphere scattering right here. So we end up with something that looks like this. We have our impact parameter here. We have our angle theta here. Then we have these two angles, these two equal angles alpha here. And so the impact parameter B is going to be equal to this capital R, which is the radius of our ball here, times sine of alpha here. So that is this alpha right here. So the scattering angle is pi radians minus this 2 alpha. And so if we sort of do some algebraic manipulations on this, what we will end up with is this right here. So we're alpha being equal to pi over 2 minus theta over 2. And so our impact parameter B here is equal to this R sine of the alpha here. We do a little bit of trigonometric manipulation here. So we start with this sine. We end up with this cosine right here. And so this will be our angle right here, this theta, which is calculated by this 2 inverse cosine of B over R. And so in general, a particle with an infinitesimal cross-section area, d sigma here, will scatter with an infinitesimal solid angle, d omega. And so this right here is just sort of the definition of a solid angle. So an angle in 2 dimensions looks like this, so we just have this theta here, but in 3 dimensions we have this right here. So this d omega right here is equal to this area here divided by r squared. And so that gives us the solid angle there. And so this is kind of what we were talking about, where we have this d sigma right here. We see that so I've sort of colored in this section here that's kind of the infinitesimal area through which particle beam could move here. Then we end up with this d omega right here. So this is the d omega right here. This d omega, so it's we're kind of moving around this circle here, d phi right here. And so that's why it's dependent on this d phi right here. So our d sigma and our d omega are proportional with the proportionality factor of this d theta right here. So the size of this d sigma here and the size of this d omega here are going to be proportional, and they will be related using this proportionality factor right here. So the d sigma is equal to this d theta times this d omega here, or we can have this d theta be this d sigma of d omega right here. And so the azimuthal angle, this phi, will be the angular perpendicular to the projectile path. So we see that it's sort of the angle that's kind of going around the projectile path there. So we have that the area of the circle at radius b is equal to this. So for our d sigma is b times db times d phi here. So we're looking at the area of this circle, this entire circle right here. Then for the d omega here, this solid angle, it's the sine theta times d theta times d phi. And so that's looking at the area of this whole circle right here. And so we want to get that the d theta here, which remember is this d sigma of d omega. So we just take these two things here and divide them like this. And so we end up with this right here. So it's equal to this b over sine of theta times this db over d theta. So the total cross section is then the integral, which is sort of the continuous sum of all the solid angles. So now we're taking this sphere here and we're sort of summing up all of the circles as we go around that way. So we're going to sum it up using this continuous sum here. And so if we had, say, a hard sphere, then we would have the sigma be equal to this r squared over 4 times the integral of this d omega, which is equal to this pi r squared, which is just the cross-sectional area of the sphere. And so it's just the circle that you would see if you're facing a sphere. So you're looking at a sphere here. So we have a sphere here. If you are just sort of looking at one side of it, all you see is sort of the half of it that looks like a circle, and so that is the sort of circle that we are getting right here, this pi r squared, and that is the cross-sectional area, because that is the part of the sphere from which our projectiles can bounce off of. They can't really bounce off of the back of it here because they're coming from this side here. What we will actually see in the case of quantum scattering is that the back of it does actually kind of matter, but we will get to that when we get there. All right, and so we also have the luminosity, which is just the number of incident particles per unit area per unit time. And so you can think of that. So say you have your large sphere right here, and you are bouncing things off of it, and you have stuff bouncing off of it. You're shooting a beam that is some area there that is determined by the d sigma, and so you're going to have things coming and bouncing off of it at all these different angles here, and so we are going to be interested in the number of things that we're shooting at this, so going through this area here per unit time, and that would be called the luminosity, which you can think about why they would call it luminosity, because you were thinking about like just shining a beam of light on it. So a beam of light that's this thick right here, you're going to shine a beam of light on it. So you're going to think about the number of photons going through sort of a area right here per unit time, and that would be sort of the brightness of the light. So we could think of, maybe we have our bowling ball here and we're shooting BBs at it, and so the luminosity would be sort of the number of BBs you're shooting at it per unit time, or the number of BBs going through like a circle here, so an area there per unit time. And so the luminosity is represented by the script letter L here. So the number of particles entering the area d sigma here per unit time is then given by this dn here, which is the luminosity times that area there. And so the luminosity, remember, has units of incident particles, so per unit area per unit time. And so you multiply that by the unit area and you just get particles per time, so particles per second or whatever your units are. And so when we rearrange this a bit, we end up with this right here. So this d theta equals this 1 over L times dn of d omega here. And so in the Griffiths textbook, he says that this is sometimes taken as the definition of the differential cross section, because it makes reference only to quantities easily measured in a laboratory. So if the detector subtends a solid angle d omega, and so remember our d omega was this right here, and so he's saying that if we have like a detector that is looking at all particles that would come off, that would bounce off of this right here at this angle, represented by that that dark blue right there. So we have a detector that's detecting every particle that sort of passes through that area. Easily measured. So if the detector subtends that solid angle d omega, we simply count the number recorded per unit time, which is the event rate, this dn here, and divide it by the solid angle d omega, and then normalize it to the luminosity, because if the number of particles sort of passing through this area doesn't tell you much unless you know sort of how many particles are actually coming and bouncing off of this thing. I think I drew this circle here, but it's actually bouncing off of that right there. And so we have a detector that's measuring all the particles coming through that area right there. But that doesn't tell us much unless we know how many particles are being, sort of fired at this object right here. And so we divide that by the d omega, and then, like I said, normalize it to the luminosity of the incident beam here. And so that is classical scattering theory. So to take this into the quantum realm, so we have the incident, we now, instead of having an incident particle, we have an incident plane wave. And so we're traveling in the z direction. So we look down here, we've defined it so that z is pointing that way. And we have right here our incident plane wave, which is this a e to the I k z. So this would have an amplitude of a right here, which runs into a scattering potential, which we have here in this red dot down there, thereby producing a spherical wave. And so the spherical wave would be this right here. And again, we would have the amplitude on there of A, because the amplitude can't change, because between the incident and the scattered wave, because so that's why we have that there, because there has to be a conservation of probability here, just like like if you're thinking of like waves on water, there has to be a conservation of energy. There also has to be a conservation of probability here in quantum mechanics. So you'll probably notice too that this is in Cartesian coordinates and this is in spherical coordinates. So we will address that probably in the next video. But just sort of for illustrative purposes, we can see that we can have this this plane wave incoming, the incident plane wave, and then the scattered spherical wave here. So yeah, the other thing to notice, we have this f of theta here, which is the scattering amplitude. So we then have to find this scattering amplitude here, which is the probability of scattering in some direction theta. And so it's related to the differential cross section. So the probability of a particle with velocity v passing through the area d sigma in time dt is going to be equal to this right here. So our a squared times v times dt times this d sigma right here. And the probability that the particle scatters into the solid angle d omega is going to end up being this right here. So we have a squared, we have our f of theta squared here, so our scattering amplitude, then the v dt and d omega here. And so we combine these together, so this right here was the probability of the particle passing through d sigma right there, and this was the probability of being scattered into the solid angle d omega right there. We do some algebraic manipulation and we end up with this right here. And so we see that our scattering amplitude squared is equal to our d theta right there. And so we can see that this is related to that differential cross section right there by just squaring it here. So yeah, the square of the scattering amplitude is the differential cross section. And so, like I said, our task then is essentially to find this f of theta here. There are two techniques that we will look at for finding this scattering amplitude. So the next couple videos I'll be discussing this right here, so this partial wave analysis. Then I will discuss this Born approximation, which I probably won't spend as much time on, but I will discuss it here in a few videos. But anyway, that was our introduction here to scattering theory. I hope you found this video helpful, and I will see you in the next one.